in this module we are looking into important quantities that can be defined within any gaseous flow. Those are stagnation properties, and the other corresponding one is the sonic or star properties. We have looked at stagnation properties and looked at their applications to the compressible pitot in the previous class. So, now let us look at these sonic, or they are also sometimes referred to as the star properties. Now, what is again common between all of them is the static condition in a flow, which is normal pressure and temperature that is measured at any particular point in the flow. So, now this is known and it is defined, and the flow is moving with a velocity v. Now, if you consider the flow to undergo a process similar, it is in conditions to the stagnation process, which is a reversible adiabatic without any work. So, that means it is a isentropic process with no work being done. It is moved from any particular velocity or at that particular point to a point where the velocity becomes exactly the same as the acoustic velocity or the speed of sound. That means the Mach number from any particular point in the flow, if it was having a certain velocity, temperature and pressure, the flow will be moved to a point where this particular point is referred to as the sonic point or the star point. V star will be equal to the A star at that particular point. So, now you should understand, now it is an isentropic process. So, as the process is going on, we have seen in the previous classes on stagnation temperature also, but more easily it can be seen on this TS diagram that as it goes towards a certain point, its temperature is changing. That means, if its temperature is changing, its acoustic speed is also changing, that is acoustic velocity is also changing. And now we are looking for that particular point where the velocity during the process as it is going is equal to that of the acoustic speed at that point. So, that means Mach number will become equal to 1, or this particular condition is known as the sonic condition. So, star condition, sonic conditions are synonymous to each other. Now, in this graph that is shown over here for a template or case, typical case, Mach number is taken as 1.5. That means, if the flow has to go towards Mach number equal to 1, it should be decelerated. Okay, so, it is decelerated and the direction is same as that of the stagnation temperature. So, stagnation temperature also is a deceleration of the flow to 0 velocity, while for this sonic process or star process, it is moving towards the sonic condition where the Mach number will become equal to 1. But now if you consider that the flow is subsonic, for example, let us take Mach number is 0.5, then the flow will be accelerated to the sonic condition. So, if it has to get to sonic condition, it will get accelerated. So, it is quite different from stagnation process in that sense. Stagnation process is always the flow will be taken to 0 velocity, whether it is subsonic or supersonic. So, there will always be an increase in pressure and temperature. But on the other hand, if it is subsonic case and then you are getting to star condition, you would see that actually the pressure ratio will decrease. Similarly, temperature ratio will decrease. but on the other hand in the supersonic case it will increase, because there it is a deceleration process. Now again, what is the equation that one has to look at? So here the process is again isentropic, and no exchange and no heat exchange or no work done. So we look at H1, again the energy equation, H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Now we directly go and apply the perfect gas calorically perfect gas assumption over here, and H is CPT and H star, that is the enthalpy at the sonic condition, is CPT star. Okay, so you get the equation here that CPT V square by 2 is equal to CPT star plus V square by V star square by 2, but V star square is nothing but A star square, which is the definition of a by definition of the sonic point or the star point. And if you put that into condition over here, then this becomes A star square, and then that is the condition that we have to really solve for. But there is also the other way to look at this process or these equations to get to the stagnation properties, sorry, the star properties. That is, consider, since both these processes are isentropic process, they would fall on the same line, and that is the starting from the given Mach number. So according to the TS diagram over here, so it is on the same line. So and stagnation temperature and pressure for an isentropic process will remain the same. So if one has to look at, say, P2 by P1 in an isentropic process, this can be written as P2 by P0 by P1. Okay, so what we are looking for really is that point where the flow goes to Mach number 1. So if we can find out what is P0 by P star, then this can be used to determine the star conditions for a given flow at that particular Mach number. And this is easily done by substituting m equal to 1 in the equations for T0 by T, P0 by P and rho 0 by rho, and you get these equations. T0 by T star is gamma plus 1 by 2, P0 by P star is gamma plus 1 by 2 the whole power gamma by gamma minus 1, and similarly rho naught by rho star is gamma plus 1 by 2 the whole power 1 by gamma minus 1. So these three equations tell you how the stagnation process and the star properties, they are related to each other. Now let us see for any given point how we can compute the star condition. That is really straight forward once this is defined, because you know this is the relationship. P2 by P1 is equal to, so if you are looking at P by P star, this is P by P naught multiplied by P naught by P. P naught by P is known, this is gamma plus 1 by 2 whole power gamma by gamma minus 1, and P by P naught or P naught by P is also known, 1 plus gamma minus 1 by 2 m square whole power gamma by gamma. So that you can represent this by this particular equation. Similarly, T by T star, that can also be represented by the same principle, T by T naught by T star. The equation that we had just seen, that is of the star energy equation or energy equation, where V star is considered and to be A star, can be taken forward, and we can define a new kind of Mach number known as the star Mach number. It has its utilities, and we will see what its significance is. And continuing there, you can, this equation is written by using the point that at star condition V star is equal to A star. And B, to re-emphasize this that it is at that particular point this acoustic speed is the same as the velocity. The acoustic speed and the velocity both change during the process. So when velocity changes, acoustic velocity also changes. There will occur a particular point where both can become the same. That particular point is known as the sonic point. Now Cp is gamma r by gamma minus 1. So gamma r T star is nothing but A star. So you can substitute that with A star. Now this can be, this is algebra, you can do the algebra, you can get it as gamma plus 1 by 2 by gamma minus 1 A star square. Now then we can define a new Mach number, that is V by A star, if you divide the entire equation by A star. So this V by A star is referred to as star Mach number or M star, and you can do the algebraic manipulations. See here, you get you have divided the equation by A star and simultaneously multiplied it by 2. So you get 2A square by A star square, this term, by gamma minus 1. This is M star square, this is gamma plus 1 by gamma minus 1. Now here in this equation, A by A star square is nothing but T by T star, and this is known, T by T star is gamma plus 1 by 2 1 plus gamma minus 1 by 2 M square. So that can be, this can be substituted here into this equation, and you can do the algebraic manipulations in this equation to come to a relation that is given over here between M star square and M square. M star square is related to Mach number M square and gamma. Now the advantage with this Mach number is that as Mach number goes to infinity, so when Mach number is equal to 1 for this case, you see that when M is equal to 1, M star is also equal to 1, because gamma minus 1 by 2 plus 1 is gamma plus 1 by 2. So M star equal to 1, but when M tends to infinity, then M star tends to it goes to square root of gamma plus 1 by gamma minus 1. So it goes to a finite number, and very soon when we discuss shock waves, this star Mach number is useful to derive relations in the shock equations. So it goes to finite values even when Mach number goes to infinite numbers. Also at this point, this energy equation can be written and manipulated algebraically to different conditions, which is useful in many gas dynamic analyses, and particularly we will see as we go on when we look at shock waves and their analysis. The alternate forms of energy equations is really useful, and that is to convert the enthalpy into using the definition of speed of sound. Of course, this is valid for mainly perfect gases. So, if you look at this, then you see that h plus v square by 2 is actually h is CPT for a perfect gas. So, this Cp is gamma r by gamma minus 1. So, you get gamma r by, so this should be gamma minus 1, this is not 2, gamma r t by gamma minus 1. Gamma r t is a square, so this is a square by gamma minus 1. So, the adiabatic energy equation without any work done, this equation can be written in terms of the speed of sound also, where a square by gamma minus 1 plus b1 square b1 square by 2 is equal to a2 square by gamma minus 1 plus b2 square by 2. Now, when you go to stagnation conditions, so when we are looking at stagnation process, then we take that the V2 tends to 0. As V2 tends to 0, T2 tends to T0. Then the speed of sound at T0 is the stagnation speed of sound, which is square root of gamma r T0. So, in this equation, then a square will tend to a0 square. So, the equation becomes a square by gamma minus 1 plus b square by 2 is equal to a0 square. The other equation that we just now came across is the star condition. So, in star condition, we saw it is a square by gamma minus 1 plus v square by 2 is equal to gamma plus 1 gamma minus 1 a star square. So, this is the other form of equation. You can also use this form of the equation, which relates any two states and their speed of sounds and velocity. So, this also is utilized in certain gas dynamic analyses. So, to look at the entire thing, we have looked at stagnation processes, which are isentropic processes that move, that is an hypothetical process. At every point you can define a stagnation point where the velocity is 0 or goes to rest, and the pressure and temperature at that particular point is the stagnation pressure and temperature. The other case, as also important, is the critical point. It is also referred to as critical point because Mach number at that particular point, where you take flow at any point in a flow, Mach number, and then through a certain process you make it go to Mach number equal to 1, which is in this case it is an isentropic process. So, that condition is known as the star condition, sonic condition. Soon when we look at the application of these principles in duct flows, you will see that this point of Mach number equal to 1 is associated with changes to certain flow phenomena itself, and there is a switch from one kind of behavior in subsonic flow regime to another kind of behavior in supersonic flow regime. So, often this Mach number equal to 1 is also referred to as the critical point, because that is a switchover point between these different kinds of regimes. So, the equations we have derived it from basic principles for a perfect gas, and also looked at how the energy equation can be written in terms of the speed of sound and velocity, and that is also useful in certain analysis that will come in the classes to come. So, in the next class we will look at certain numericals where we can apply these principles and understand them better.